Hello students, welcome to today's class. We are starting one of the most important chapters in physics, current electricity. By the end of this lesson, you'll understand not just how electric current flows, but also how resistance, potential difference, and Ohm's law work together to make our devices run. Let's start with the basic idea. What is electricity? Electricity can exist in two main forms: static electricity and current electricity. Static electricity refers to the buildup of electric charge on the surface of an object. These charges remain at rest. They don't move until they find a path to discharge. A straightforward example: when you rub a balloon on your hair, it attracts small bits of paper. That's static charge at work. On the other hand, current electricity is the flow of electric charges through a conductor. These moving charges are usually electrons that flow due to a potential difference between 2 points. For example, the flow of electric current through a wire connected to a battery. Now that we know what current is, let's see which materials allow current to flow. Conductors are materials that allow electric current to pass easily because they have free electrons. Examples include copper, aluminum, silver, and seawater.
Sir, may I ask a question? If seawater is a conductor, then why isn't pure water?
Good question. Pure or distilled water doesn't conduct electricity because it has no ions. It's only when impurities like salts are present, as in seawater, that it becomes a conductor. So, seawater is a conductor while pure water is an insulator. To sum up, insulators resist the flow of electric current. They have no free electrons. Examples: rubber, plastic, glass, and pure water. Seawater conducts due to dissolved ions. That's why we use insulators to cover electrical wires and devices to ensure safety and prevent electric shocks. Let's now talk about insulators. Insulators are materials that prevent electric current from flowing through them. The key reason is that they have no free electrons available for conduction. For example, rubber, plastic, glass, and distilled water are all good insulators. Now we move to one of the most fundamental laws in electricity, Ohm's law. Ohm's law states that the current passing through a conductor is directly proportional to the potential difference across its ends, provided temperature and other physical conditions remain constant. Mathematically, it is written as V is equal to I multiplied by R, where V is voltage in volts, I is current in amperes, and R is resistance in ohms. Example: if the voltage is 10 volts and the resistance is 5 ohms, then the current equals 10 divided by 5, which is equal to 2 amperes. When we plot a graph between voltage and current for a metallic conductor, we get a straight line passing through the origin. This straight line shows that the conductor obeys Ohm's law. The slope of the line gives us the resistance.
Sir, may I ask a question? What happens if the graph is not a straight line?
Excellent point. If the graph is not a straight line, that means the material is non-ohmic, its resistance changes with temperature or voltage. For example, a filament lamp doesn't follow Ohm's law because, as the filament heats up, resistance increases. Resistance is the opposition offered by a material to the flow of electric current. It depends on three factors: material, length, and cross-sectional area. The relationship is given by the formula R is equal to ρ multiplied by L divided by A, where ρ is the resistivity of the material, L is the length of the conductor, and A is its cross-sectional area.
Sir, may I ask another question? Does temperature affect resistance?
Yes, absolutely. For metals, resistance increases with temperature because the atoms vibrate more and obstruct electron flow. In semiconductors, the opposite happens. When the temperature increases, their resistance decreases. This is because heating provides more energy to the electrons, which break free from atoms and help in conduction. So, in the case of metals, when the temperature increases, the resistance also increases, but in the case of semiconductors, when the temperature increases, the resistance decreases. This behavior is very useful in designing electronic circuits and sensors. Resistivity is a property of the material itself. It tells us how strongly the material opposes current flow. It's measured in ohmmeters and is independent of the shape or size of the material. For instance, copper has a very low resistivity, that's why we use it in wires. Rubber has a very high resistivity, that's why it's used as insulation. Now, students, let's understand how temperature affects the resistance of materials. In metals, when the temperature increases, the resistance also increases. That's because the atoms in metals start vibrating more rapidly when they are heated. These vibrations make it harder for the free electrons to move, so current flow becomes difficult. Here are some real-life applications. Semiconductors are used in temperature sensors, thermistors, and electronic circuits because their resistance changes with temperature. For example, in a temperature sensor, as the environment heats, the semiconductor's resistance drops, and that change is used to measure temperature.
Sir, does this mean semiconductors are used instead of metals in circuits?
That's a great point. Metals like copper and aluminium are still used for wiring because they conduct well and have low resistance. But semiconductors are used where control and sensitivity are important, like in sensors, transistors, and integrated circuits. So, to summarize, in metals, resistance increases with temperature. In semiconductors, resistance decreases with temperature. Applications, sensors, thermistors, and electronic circuits use this property. That's how temperature plays a crucial role in the behavior of electrical materials. Let's quickly summarize what we've learned so far. Static electricity is a stationary charge, current electricity is moving charge. Conductors allow current to pass, insulators don't. Ohm's law gives the relationship between voltage, current, and resistance. Resistance depends on material, length, and area, while resistivity is a material property. In the next class, we'll move to series and parallel combinations, the heating, lighting, and magnetic effects of current, and power calculations. Thank you for paying attention. I'll see you in the next session. Jai Hind.